Okay. Um, we have a lot of logistics to talk about today, but then we'll talk about reinforcement learning. Um, I wanted to do like the big derivation of the PPO policy gradient, but I have to keep today's lecture a bit shorter because I have to leave. So I decided to keep it to sort of the philosophy, and then we'll do sort of the math behind PPO in the next lecture. Um, But part of the statement is that we have a engineering team coming that we're hosting at Caltech for the next 2 weeks. Um, and specifically, I'm in charge of like organizing this like long horizon humanoid navigation thing next Thursday. So I think that next Thursday will not work for a lecture. Um, in fact, we'll probably have to skip next week, and then maybe we could do Friday of the week after, or we can try to find some time. So for people who are interested, just yeah, keep in mind the next 2 weeks are a bit busy, so we might have to sort of work around that visit.
Are there events scheduled for the visit that like your talk? Or what?
Um, I the visit is very much an engineering visit. So like they have a squad of engineers who are going to pull up and we're going to like give them desks and then we're all going to work together. Um, so there won't be a lot of formal presentation. There will be demos. You're like definitely invited to come watch any of the demos. I can send in the like Slack the schedule for when those happen. Um, some of them will maybe be reasonably interesting. Some of them might be boring, depending on your level of threshold for excitement. But the one not this Thursday, or like 2 Thursdays from now, is there'll be like a filming crew. It'll be a whole big production. So in theory, that one should be reasonably interesting to watch, maybe. But also, like, once you've seen a humanoid walk, it's just going to be the humanoid walking from like one point to another point a long ways away, and then a drone flying. And so, yeah, that may or may not be exciting to you. Yeah. This engineering team is from TII, which is like the Technology Innovation Institute in Abu Dhabi. They are part of a team that was TII has sponsored like multiple millions of dollars worth of grants to Caltech over the last 3 years. This team is part of one of those grants. Um, that like one grant has been the dominant source is maybe a stretch, but like one of the biggest funding sources for my lab for the last 3 years. Okay. I will also note that in preparation for, we had a meeting that I just came from that I like was getting stuff to work for literally right before. So I'm a little bit less prepped than normal, which is going to come out in ugly ways, I'm sure, but we'll see. Um, any questions, comments, fun stuff to say before we get started? Maybe a note on where we're going. So I wanted to do reinforcement learning. I wanted to have maybe another lecture where I do a bit more of the math on reinforcement learning. Um, then there was going to maybe be another lecture on learning from demonstration. So things like diffusion, um, start with behavior cloning and the history, and then talk about diffusion policies, VLAs, um, this sort of stuff. And then that was like sort of the main core, right? We will have talked about like optimization-based control, learning-based control, and then this sort of super modern like vision or diffusion-based control. Um, maybe I would have one more lecture on layered control, and then that's kind of like the summer. I'm going to have a trip in there. There's going to be a push for ICRA, so things will probably get busy around that. So those like 2 or 3 more lectures might be sort of all that I have planned for like the immediate or for the rest of the summer. If we want to keep going, we can, but that'll sort of be up to you and or the people that you can recruit to maintain interest. Yeah,
You cover that,
sure.
and how we vote.
I think this is good. Yeah, if we get to a spot where it's like two people, I mean, I'm excited about this, but it takes like non-zero amount of time. Like even this lecture, I didn't prep for it, but I had to think about it and like, right. So yeah, it takes time to do, and I think that there's, definitely some level of trade-off for the level of formality. Like if you want to come talk to me one-on-one, we could set up a time every week to like have an informal discussion, but I'm not going to prep for that in the same way that I'm like preparing for these, if that makes sense. And that stands actually independently. If you guys want to chat about stuff, we can chat about stuff all the time. It doesn't have to be in like this formalized setting, but this formalized setting is like considerably more work than that sort of informal chat would be. Um, I'll make a note on multi-agent task allocation. Uh, do you have like a specific motivating problem?
I guess I'm just interested in, given, I guess this is a robot, so like given, some desired final configuration of robots,
Mhm.
how do you decide? Which is probably not as interesting, like, I guess like given some task you like, climb up the steps and put like the shirt and the drawer.
Yeah. Okay.
How would I opt?
Okay. Yeah. Um, yeah, it's an interesting question because there's like a vast variety of approaches all the way back from like um, they used to make their own programming languages to solve these types of problems, like task. Yeah, so this is what I mean by they would write programming languages to like formalize the exact notion that you're saying, and then you would run an optimization program kind of over the result. This is like the field of task and motion planning has done this um, for a long time. The modern approach is just like ask an LLM, and it will tell you what is optimal, and what you've traded off is like optimality and interpretability for generalizability. The main drawback of the systematic like task and motion planning style results is that you had to sort of preordain the set of capabilities ahead of time. And then a lot of roboticist type people were like, if I'm trying to program a robot to do the dishes, like I actually can't pre-compute the set of things that I need to do ahead of time. It's like much more natural language. Um, Natural language is a much more natural interface to control. And so that's why things have gone the LLM direction. But we can talk about kind of that whole um, line or lineage. Yeah. Okay. Any other thoughts before we do RL? Okay. Okay. So yeah, I wish I'd taken some more time to organize my thoughts about the history because the history here is quite interesting. Um, I'm going to start by talking about two specific institutions. So one of these institutions is the Robotic Systems Laboratory, which is a lab at ETH, run by Marco Hutter. Um, and the other one is Boston Dynamics. And I'm talking about their Spot and Atlas team. Um, Boston Dynamics is probably the biggest name in legged robotics anything. They have been around a long time, sort of starting all the way back with Mart Rayberg in like the 80s, doing hopping robots. So they had like single leg robots that would bounce. And this was a really good case study in dynamic stability. And dynamic stability is sort of critically important when we are dealing with systems with legs, and less important when you have systems that have wheels, which are statically stable, things like this. Um, and then RSL is a very predominant lab in the field of quadruped robotics. They built the Animal robot, which is maybe Spot's main competitor for not low cost, but like very, very high quality quadruped robots. I would say those are the two main ones. They're like above the Unitree Go 2 in terms of quality, but also in terms of price. Um, and the reason to bring these up is that these two labs were like pioneers on the forefront of the use of optimization-based methods to control like very complicated systems. Right? So um, RSL has a ton of results on model predictive control for the quadrupeds. Um, they do very, very impressive things, including integrating with perception sensor data, planning footstep locations, um, reduced order MPC, full order MPC, all this sorts of stuff. And then Boston Dynamics used MPC as their main control methodology for the Spot and Atlas humanoid, like really deep into the game. I might be knowing more about the Atlas evolution than most people, but the original Atlas robot was driven by hydraulic actuators. So actuators that rely on like hydraulic fluid to generate force. Um, and this is very interesting because it made their robot different than like any robot still that has really ever existed in sort of the mainstream media. But the hydraulic actuators have much, much higher power density than standard electrical actuators. But the downside is that they are very difficult to model. Um, and they're sort of difficult from a mechanical engineering perspective. You have hydraulic fluid running around. This is like a nightmare. There's videos of them like breaking a tube on that robot and like the fluid like flying everywhere. So it's a bit of a nightmare. That robot just got retired at like the start of 2025. And all the way through the lineage of that robot, they were doing primarily model-based techniques. Um, so these are two institutions that I would say they started like all of model-based control for legged systems. They brought that up from the ground. There was pretty much no ability to control legged systems, and then these two were two of the people that were at the forefront for like bringing that up from scratch. Um, and then RL started to become popular. Um, Actually, maybe one of the biggest breakout papers for reinforcement learning came from the RSL lab called Learning to Walk in 20 Minutes, which Marco Hutter presented at a conference where he started a RL training at the start of his presentation and had a robot like on the side that was just like live executing the current policy that the RL was like had learned how to do. And at the start, it was like stumbling around, couldn't do anything. And then by the end of the talk, 25 minutes later, it was like navigating or like walking around these blocks and stuff, like putting its feet on the blocks. And um, one of the like a very, very cool talk. I'd recommend going and looking at it if you haven't seen it. And now if you go to either place, the model-based sides are completely dead. Um, so basically we had like 1980 to like in the case of Boston Dynamics, literally like 2025 as like MPC was at least a dominant force or something that was really, really considered. And, this is maybe 2022 to 25, depending on who you ask. And then now, I mean, I think it is so dramatic as to say that like MPC is no longer researched at either institution. Um, so both of those places that have an immense history in model predictive control and sort of optimization-based methods have completely switched to reinforcement learning. Um, there's a lot of potential things to take away from that. One thing that I would say is positive is that both of these institutions did a very good job, maybe a reasonably good job, of remaining flexible, right? Something that people tend to do is they get very attached to the method that they are currently working on. We all do this. I think it's very natural. And you tend to then, instead of sort of sitting back and evaluating like what the best method is for your problem, and that's maybe a re-evaluation that you want to be doing periodically. You can't be doing it all the time, right? You do have to commit and like just go do something. And I'm personally a proponent of kind of committing and almost putting your head down, right? Just like pick something and then do it really aggressively. But every now and again, you do need to pick your head up and give the field like a fair reevaluation. And both of these were places that did that very well, right? They had a bunch of tooling for MPC and they were willing to be like, look, there's this other method that's great. We're going to adopt that method. And then look, now our stuff is even better. So I think one thing to take away from this is just like, wow, they did a good job being flexible from a research perspective. They didn't get stuck doing their one thing. They were open to change, and now they're leaders in the field of reinforcement learning as well. Um, to be fair, they were a leader in the field of reinforcement learning the whole time, but Boston Dynamics at least was not, and they sort of transitioned pretty late. The other thing that I sort of want to glean from this is just why did this happen, right? Um, and there's one pretty critical sort of parallel, which was the release of Isaac Sim. So we already talked about simulators, but this transition, especially for the RSL people, was highly correlated with the tool Isaac Sim being good and readily available. And the reason this was important was because Isaac Sim was one of the first GPU-based rigid body simulators. And so we had a huge speed up in terms of throughput. Right. So we talked before during the simulation lecture about how throughput is one of the things that a simulator can be measured or evaluated on. And, this whole MPC chunk, there just weren't simulators that gave you good enough throughput in order for reinforcement learning to be a viable technique. So throughput is one thing, but I'm going to argue that throughput alone doesn't say why RL wins. That just gives us a sense of the timeline, right? Like when we made this throughput jump, now we were able to have a competition. You could actually compare RL and MPC sort of in their current forms. Before that, RL running on a CPU was just a lot slower, and it took a lot more time to collect data sets. So it wasn't quite as mature. I mean, reinforcement learning really exploded in 2015. So we're talking about it took from, Min et al. In 2015 solving the Atari game set, like 5 to 7 years before Isaac Sim came out. Now we can simulate these rigid body complicated systems in parallel, and then that blew up. So things have happened relatively quickly. But there's other reasons I think that RL has like really gained a big advantage over MPC. And also I'll kind of list a couple of them. Okay, an unfortunate one, but a true one, is ease of implementation. Uh, Model predictive control, kind of like we alluded to last lecture, requires a lot of very specific knowledge in order to make this work, right? We need to know, first off, how to write down an optimal control problem that does what we want. For legged locomotion, that's really, really, it's pretty complex, right? The optimization problem is. And then we need to go to solve the optimization problem. And so we also have to be an expert in numerical optimization. Uh, and then we need to get the numerical optimization to run in real time. So there's the real-time iterations component. We're going to have some really aggressive SQP. Everything is going to be very approximate. Getting that thing to run is sort of very hard from a code implementation perspective. It's a lot of work. And now RL is also a lot of code, but the difference is that a lot of it is boilerplate, right? A lot of it is code, PPO is an algorithm that you can just take online, or like, you can git clone it and run it. That doesn't really exist for model predictive control. You can't just like git clone somebody's model predictive controller. Everybody has to pretty much roll their own for every system, because the tweaks that you'll need to do in order to get it to work for your system are difficult. And so the ease of implementation for RL led to a lot of these tools that anybody could use, right? So there's like generally available tooling, right? And then the tooling lets anybody try it. And now when anybody tries it and you have way more people trying RL because the barrier to enter trying is so low, there's going to end up being a lot more people that work on it. So one part of this big transition was just that you had a tool that was a lot easier to interface. You end up with these big public implementations like RSL, RL, the OpenAI like gym environments, sort of all of these things. This just like lowers the barrier to entry, and it's a lot easier to get people working on high quality projects. Um, Another one is the modeling requirements. So for model predictive control, there's a lot of modeling requirements, or at least modeling decisions that you have to make, right? We haven't gone into sort of super detail about how these model predictive control schemes were run, but a lot of them, that they're not run often on the full order dynamics, right? They're going to be run on like a centroidal dynamics model, or some spring model of the system, or one of these other things. And so there's like so many different ways that you're going to parameterize this model, and every one of them is going to give you a different controller that you have to tune. It's a nightmare. Furthermore, we talked about how not only did you need to maybe pick a model, so for MPC, we need to pick a model. We also need to be able to compute gradients if we're going to use a gradient-based solver, right? So things like contact are going to be really, really difficult. So we need to pick a model. The model needs to be analytic. It needs to be differentiable. If it's not differentiable, we need to do a bunch of nonsense in order to solve it with a gradient-based solver. Whereas when we look at RL, there's actually, and I want to make this point sort of clear, there is no constraint on the model that you need for your system. Some people might say you just need a simulator, but I'm going to argue you actually don't even need a simulator. You just need data, right? And data is not a model. You literally only need sort of the data that comes from rolling your policy out. And this is typically done in a simulator, but it's actually possible to do this directly on hardware as well. there was a period of time where Google started standing up these massive robotic arm farms, like thousands of KUKA arms that they were going to try to run reinforcement learning directly on the arms themselves. So not like running RL in a simulator, but running reinforcement learning live using the arms to collect data. And so when I say that, Isaac Lab allows me to scale to 4,000 environments at once, they were like, well, let's just buy 4,000 robots, and then we can do the same thing. You can throw out the simulator and the model. You can actually just collect the data sort of on hardware. And okay, this experiment actually failed, but not because RL is not good. It's because they were trying to apply the problem to dexterous manipulation, and dexterous manipulation is hard. So my point with that story is really just that some people will say that RL requires a model because you need a simulator, and the simulator is your model. People will sort of make that. But we should remember that PPO does not require a simulator. It doesn't require a model. It just requires access to state action transition pairs, which we'll get to when we talk about the problem statement. Those can come just literally from the system. So you don't need a model. You just need access to state action transition pairs. And that is like a way more flexible regime, right? We don't have anything about contact or gradients or any of that nonsense. We like just need access to the data generated by execution of the system. Okay. I'm gonna excuse my board management, come down here. Okay, another really big one was ease of integration with perception. So if you think about you have a legged robot, let's say, and you want to do some perceptive locomotion. So now I have things that are not just flat ground. There might be stairs or potholes, things that I can step on, things that I can't step on. If you want to use model predictive control to do that, you very quickly are going to end up with first off, you need to use sensors to identify the places on the ground that you can and can't step. And then you need to pass those areas in a way that the MPC can understand, right? So if I have a set of stairs and I think about what happens when I get like a LiDAR scan back, right? My LiDAR scan is going to be a bit noisy and it's going to return like points that look like this, right? So I'm going to get some like noisy point cloud that looks something like that. And I need to pass a constraint to the MPC problem that says like my foot location at contact needs to be in one of those intervals, right? So I need a map that takes in the green point cloud and spits out an OR constraint, right? Where maybe I express each of these as polytopes. So this is going to be like A1x less than or equal to B1. And this one's going to be A2x less than or equal to B2. And then when I go into my optimization, I'm going to enforce that the foot has to be in one of those polytopes when I make contact with the ground. And both parts of this problem are hard, right? First off, going from the green point cloud to these like red sets is not easy. There was a lot of work that people did on this. I'm not going to go into any more detail, but I'm just going to say that at the very least, we should admit that that problem was reasonably hard. And then once we had solved that problem, our optimization now became mixed integer. Mixed integer meaning we have like a discrete set of constraints of which exactly one should be active. And so the way that you would solve something like this would be basically you have all of these constraints and then you have an integer like 0, 1, 2, 3, 4, and your optimization has to pick that integer and then enforce that constraint. Notably, we'll note that that sort of optimization is like definitely not differentiable, right? This like decision of which of these constraints to enforce is very much a discrete decision. We can't like partially enforce one constraint. We can't perturb which constraint we're enforcing. So there's no notion of a gradient. Um, that optimization problem becomes very much harder. So when we wanted to take MPC and integrate it with perception, the problem was already difficult and it's exploding in terms of compute requirements and complexity and everything like that. So, so for MPC, I'm just going to say that at the very least, this is hard. For RL, you can just pass in the sensor data, right? So people would just take a depth image, like from a depth camera, where they would take in a LiDAR scan directly into the policy and let the policy learn all of this nonsense, right? So the policy is going to learn where it can put its foot. The policy is going to learn how to handle the mixed integer nature of this sort of complicated environment. Um, so I'm going to write easy. Of course, this is not easy. There's like a lot of things you have to do, but sort of at least in terms of conceptually, in one, we have this like entire engineering stack that somebody is going to have to stand up and maintain in order for you to segment your environment into steppable locations. And then you have to make your optimization problem way worse. Or over here, you just ingest the sensor data directly. And one of those is, again, much easier from like the implementation perspective. Okay, and then there's a lot of other things too, right? Like we have MPC has you pick a model. And so what happens when the MPC model is actually wrong? Well, you need the MPC to be robust to that. There's not a lot that you can really do to like robustify the MPC. You can for linear systems or in special cases, but if you have a complicated system, you need to do a really good job of getting the model right. Whereas in RL, it's like actually we just sort of domain randomize and it's like kind of fine. Um, the idea being that, okay, there are sort of statistical techniques that we can do to relax the accuracy that we need of the model in order to still get really good performance. Um, the list kind of continues on. So the point of part one of this is just for me to say, look, if you don't know these two companies and you're interested in reinforcement learning, you should go look them up and you should be familiar with sort of their top people and their like paper lineage, I think is a very good demonstration of this like optimization based to control to RL control arc. And then as far as why that arc occurred, I think it has a lot to do with some of these things that I've talked about, things regarding ease of implementation, um, regarding the modeling requirements, and then integration with perception and some of these other things. Yeah, yeah. We'll do versus optimal control problem when we like write down the statement. We'll show very explicit parallels. Yeah. Any other questions? Yeah. Yeah. It's a really good question, actually. Um, I don't have a great answer, so I'll say that I don't know. You know, I wasn't there. Um, part of it is that they tackled a hard problem, right? They were trying to do sort of dexterous manipulation, and dexterous manipulation remains a problem that has seen only moderate progress due to reinforcement learning and much, much more progress due to imitation learning or learning from demonstration. Um, now, the reason that I say that that answer alone is not satisfying is that the main reasons that uh, lag dexterous manipulation from the perspective of pure RL are actually exactly solved by just doing it in the real world rather than in simulation, right? Some of those main drawbacks are to do dexterous manipulation, you don't typically need to condition on an image. There's like really no, there's not another sensor that can replace vision. Um, LiDARs are typically not going to be like high enough point density. You could try LiDAR. I'm sure people do LiDARs, but the sort of standard approach is that the pixels in an image are just such a more rich representation of the world that it's like really one of the only things that typically gets used for dexterous manipulation. So now if you want to do that for reinforcement learning, you need photorealistic sim. That is going to kill your throughput at the very least, but also just photorealistic sims are not yet perfect. They're not phenomenal. One of the other problems is that dexterous manipulation is one of the most contact-rich things that we do in robotics. So now the fact that you're like making all these sacrifices on contact modeling in order to get that throughput, they're going to come back and bite you more in dexterous manipulation than they are going to in locomotion. But you know what's a really good model of contact is the real world. So like they also had that working for them. They should have been able to really leverage the real world contacts. Um, so really maybe one of the biggest things that hurt them was just that they were too early. Like I think a lot of these techniques were reasonably young, and so things have grown a long way since then. But that might be an interesting thing for me to look at more. But I certainly know that Google owns these ARM farms that are just like dormant. Um, so yeah, there are, I think RL is starting to tick up again in terms of the dexterous manipulation community. There's more people doing it now than there was, but it's still super dominated by the sort of learning from demonstration space. Uh, Although still, I think the manipulation with the dexterous hand, not just the like the grippers, is very much a massively, I mean, all of these are open problems, but that one is like there's not even people with decent results. You know, the grippers is where a lot of the learning from demonstration came from because they're easier to collect data on. You can have somebody literally like pinch the gripper themselves, whereas you can't have somebody control a multi-finger hand, and we're not yet good enough to use an actual demonstration of a human using their hand in order to control like a dexterous hand on a robot. So yeah, yes. But those policies actually typically don't deploy with dexterous hands. They will deploy on these like parallel gripper, um, sort of two-fingered grippers. And the reason for that is just that dexterous hands are very, very hard. There's high degree of freedom. And then typically, because you have so many actuators and everything else in there, there's a lot of like rigid contacts. Um, Whereas these grippers will typically be flexible. And so you'll have them pinching things. The flexibility will give you a lot of like adaptation in the contact and all these other things. Um, so most of these pipelines will end up still being deployed on robots that work like that. You are right that they are spending actually huge amounts of money to pay people to just put a camera on their head and collect data. Um, but I think it's still very much an open problem to take that data and then use it with like an actual dexterous hand. And I would say that at the very least, that's like not the approach that a lot of them are working on. There are certainly companies that do this, right? Like Figure, all of Figure's robots have articulated hands. I mean, all of the humanoid robot industry does have articulated hands. But a lot of the like sort of fundamental breakthrough problems in diffusion and like learning from demonstration, Tedrick and sort of all of these other like TRI papers, which, 2023, 2024, the foundations are now like 2 years old, maybe. Those were all on these parallel grippers. And they're doing things like changing bike tires and using tools that are sort of very dexterous in terms of the quality of their manipulation, like a lot more than, picking up like a crumpled up piece of paper, which is what Figure is still, doing in some of their demos. Yeah. Okay. Are we ready to move on to the problem statement? Let's start by just writing down the optimal control problem again. Okay, so we have our cost functional that takes in an initial condition and an input sequence. And so we're just going to write this cost functional as an infinite horizon integral over some stage cost, C, subject to we have the dynamics constraint and input constraint. Um, sorry, these constraints should go here for the optimization problem. This is just the definition of the cost functional. And then our value function is what we get when we minimize the cost functional over our control trajectories U. And that was really the focus of last week's lecture. Um, any refreshers necessary on the statement of that problem? Are we clear on that? Okay, then we will move to the RL problem statement. Okay, so there's a bunch of ways to write down the RL problem, but the problem is formalized. This, I've formalized the problem as an optimal control problem, so I'll write OCP here. RL is formalized as what's called an MDP, or a Markov decision process. And maybe even a partially observable Markov decision process, but we'll start with just the Markov decision process. S here is going to be the state space, and A, the action space. So we'll note that the state space is quite similar to X, the action space similar to U. I'm going to stick with the language of the reinforcement learning community over here and sort of call out the parallels to the optimal control problem. Um, T is what we'll call the transition function, probability, whatever you like. And the idea is that T is a map from S cross A to potentially a probability distribution over S prime. Right, so basically what we'll say is that often this is written like this, where we say T of SA, S prime is equal to the probability of ending in S prime, given that we started in state S and took action A. So already we've injected probabilistic dynamics here. If you have deterministic dynamics, that's okay. This sort of just collapses to an indicator function. But again, these transition dynamics are parallel of the continuous dynamics F or discrete dynamics F over here. Yeah, correct. Yeah. And you'll note that we're sort of accepting a discrete time stance here. Like we're starting in S, we're taking in action A, and we're ending in state S prime. So there's not necessarily the notion of an ODE that we can at least start with when we write down the optimal control problem. Okay, and then our last one, R, is the reward. Um, where R maps from S cross A to a scalar real. So we're going to say that R of SA is equal to the reward. Okay, so we'll note that T was very similar to the dynamics F, and then R, the reward, is sort of semantically quite similar to the cost, the stage cost C. Okay, are we clear on the setup for the RL problem? Good. Stands for Markov decision process. The Markov decision process is basically like not including the reward part. An MDP is basically this notion of stochastic dynamics where this transition probability only depends on my current state and my current action. So a process is non-Markovian if we need more history, let's say, or information other than the current state in order to determine what this transition probability looks like. So a sort of the easiest example is just something where the next state depends on like a history of the previous states or something like that. That's an easy way to break the Markovian sort of assumption. Um, okay, clear? The sort of one thing that I'll note is that depending on your formulation, sometimes we will also take in O here, where O is the observation. So O is basically a function of S. It could even be, again, a probability distribution, or it could be a deterministic function of S. But if you have an observation O, then you're going to end up with what we call a POMDP, or a partially observable Markov decision process. And in this case, the agent receives the observation O rather than the state S when it's making its decision. So we'll talk about the decision-making process in a second. But this is very common, right? Like you have sensors. Sensors tell you some things about the world, but not all of the things about the world. And so there will be a lot of states S that are hidden. You can't actually see them. And so it's still a Markov decision process because the state determines where you will be, but you cannot necessarily determine where you will be just from your current observation. So that makes the control problem a lot harder because the observation sort of isn't enough to back out what's going to happen to you next. But this is sort of the main framework that you will typically actually end up with reinforcement learning, but we can really talk about it sort of in full detail just from the MDP and to note the observability gap when necessary. Okay. Okay. So the next question is kind of what is the goal, right? The goal over here is to sort of minimize this integrated cost. And the goal in reinforcement learning is going to be sort of the opposite. We're going to define a function R, which is equal to the expected, because now our dynamics and sort of everything associated with our problem is stochastic. So we can't just compute an integral because we don't actually even know where we're going to end up, or it sort of is a random variable. So we're going to be dealing with expectation instead. And it's going to be the expectation of the sum over some infinite horizon of our rewards. And what's the problem if we just sum the rewards as is, as opposed to, okay, let's say for optimal control, we've said that our cost function is positive definite. Sorry, meaning that the cost at 0, 0 is 0. So when we take the integral, as long as we converge into the origin, that integral converges. How does that compare to this reward sum? We don't have any notion that this reward sum is going to converge, right? And so the way that this gets handled in practice is that it's actually going to be a discounted reward where we're going to introduce, whoops, that's not close to a gamma. Gamma strictly less than 1 as the discount factor. Okay, so we're taking the reward at each state, and then we discount the future rewards exponentially. That exponential discounting ensures that this sum is always going to converge. And then we'll talk about like what we're taking the expectation over in a second. Yeah. Say again. Yeah. Typically, gamma is fixed for all k. I just say typically because I've never seen it and don't particularly see an advantage, but you could have a gamma k schedule. It would just make your life way harder for limited reason. Typically, people will pick gamma values of like 0.95 or 0.99 are common choices. They're going to be close to 1 because you don't really want to be discounting, but you do have to discount in order for the problem to sort of be mathematically well posed. Okay, and then the question is sort of what are we taking the expectation over? And this is conditioned on, say, like S is 0, right? The initial state. And the expectation is typically written as something like this. We're taking the expectation over the policy, where now we've introduced the policy. Um, where the policy is now sort of here. If we're thinking about the feedback controller that we get from optimal control, it's deterministic, right? If I am in a state X, the optimal controller will give me the best action to take U. In the case of RL, that's going to be the policy will actually also be stochastic. So this is now going to be the probability of taking action A in state S. And so now when we take the expectation, we're taking an expectation over this probability distribution and then also over this stochastic transition probability distribution. So we could roll them out forward and then basically, you know, approximate this expectation numerically. Yeah. It's not, I'll push back like the framing of convergence guarantee. We're not doing it just so that we can guarantee convergence. Uh, that converging is like necessary for the structure of the algorithm, right? So it's more of a, I would say maybe the term I would prefer is well-posedness as opposed to like convergence guarantee. But I think the sentiment of what you're saying is exactly correct. We introduce that discounting term literally just so that this sum stays finite, because if it goes infinite, well, then the problem sort of is not well posed anymore. Yeah.
Other cases where like maybe it goes to reverse, care about the rewards that are down the line. Sorry, war.
Yeah. There's a big problem with caring about the rewards in the future more than now, because that can lead to inaction. So if you care about the rewards in the future more than you care about the rewards now, oftentimes the optimal thing to do will be to do nothing. And then when you take one step forward into the future and you like run the optimization problem again, the optimal action will again be to do nothing because since this is infinite horizon, our problem is stationary. It doesn't actually depend on time. So we typically don't want to weight the future rewards higher unless we are in a finite time regime, then it is okay to do. So if we're saying that my entire episode is going to play out in t seconds, then we can actually weight the episodes in the future forward because our problem will not be stationary. The like policy will end up depending on time and you can get around some of that. So if you, for instance, if I wanted to enforce like a terminal constraint in a finite time optimization problem, what that ends up being is like basically a reward that has a huge amount of value at the end and not a lot of value at the beginning. Now, typically we don't enforce that with gamma, but I will just say that you're sort of thinking correctly that it is okay sometimes to have rewards that are sort of in the future. But I will say that the proper way to do that is not via like this gamma term, but actually just to have this reward function like depend on time. Yeah. So typically you'll see people sort of taking it as close to one as possible while keeping the numerical stability of the algorithm. Because if you take it too high and this thing sort of gets really, really large, then you can get all sorts of numerical stability issues. But when you make it smaller, stability goes up, but you're running into this discounting problem where you're sort of explicitly not considering rewards far in the future because you're weighting them less.
Like there's no way that R grows fast. Yeah, shrinking.
Yes, if you had a reward function that grew super exponentially, this would be bad. There's not a lot of super exponentially growing functions, so typically we're pretty okay. But if your reward was like factorial of 1 over distance from the goal or something, then yeah, that could be a problem. Yeah. From a sort of theory perspective, typically, yeah, just saying that R is bounded is enough. But practically, oftentimes, we will pick functions R that have very specific shapes. We can talk more about that. I don't think we're going to get to like implementation details today, but maybe we can get to implementation details next lecture. And it turns out that like oftentimes people will use functions that look like this, which is like a bell curve sort of normal distribution shape. This is a very common reward shape. The reason for that is because it's nicely smooth differentiable. Odd, like RL doesn't really care about that. But it still helps solve the optimization problem to sort of keep your rewards smooth. Turns out that this same form actually comes up a lot because it's a really standard way to take a cost, right? Like norm of the error is a typical cost that you would put in an optimization problem and turn it into a reward. It turns out that this like norm squared and this exponential have like the same but opposite Hessians at the origin. So they're functions that look quite similar and behave quite similar in an optimization problem, despite one being a reward and one being a cost. Yeah. And then notably, this is bounded between 0 and 1 to tie it back to your question. Okay. And I'll rename this, we'll call this V of S. And specifically V pi of S. So this expected discounted return is what we now call the value function. So we had a value function for the optimal control problem, which was the sort of infinite horizon integrated cost, and we now have a value function for reinforcement learning, which is the expected infinite horizon discounted return. And our problem is now basically choose our policy pi to maximize the value function under that policy. Typically in optimization, we are not optimizing, or often in an optimal control problem, we don't really phrase it as optimizing over policies, but rather as optimizing over input sequences. And so that's why U was an argument to J there, and then we did the min over U. In this notation, we can view pi as like an input to V, and then we're maximizing over pi. So instead of optimizing over like raw input sequences, we're actually going to optimize over the space of like feedback policies. Okay. We're already running up against my shorter time constraint today, so just a couple more statements. In addition to the value function, I'm going to introduce another term, which is called the action value function. So the action value function basically gives us like a one-step look ahead with regards to the action A. So the action value function basically says where the value function says what's my infinite horizon discounted return sort of under the current policy given the state that I'm in. The action value function says given the state that I'm in, if I choose to take the action A, now what is my infinite horizon discounted return? So it's kind of like taking the value function and conditioning it on the action that you take right now. And then this gives us access to one other sort of critical idea. Which is the advantage. The advantage, again, is computed with respect to a specific policy. And the advantage is trying to measure how much better it is to take the action A in the current state than it is to follow the policy in the current state. So how much better is A than the policy pi, right? And so the idea is that if you executed the policy pi, you would end up with V pi of S. But if you take the action A, then you're actually going to get a return measured by the action value function. And so when this advantage is positive, that means that the action A is actually better than your current policy. And if it's negative, it means that the action A is worse than your current policy. And then sort of notably, if you take the expectation of A over actions sampled from the policy, you return 0, right? Because when you take the expectation of this, it collapses just exactly to the definition of V pi of S. And so then you end up just taking V pi of S minus V pi of S and you get 0. So the distribution of actions that come from the policy sort of definitionally gives you no advantage, But if you consider other actions, then you can see actions that are doing better or actions that are doing worse than sort of your current policy. We'll note that sort of once we got past the value function, these things are notions that are more internal to how we're going to think about the algorithms that RL run. They don't really have exact parallels to the optimal control problem anymore. Okay, that is sort of the problem statement as I'm going to leave it. And like I said, we'll get to sort of using all of these definitions to derive different policy optimization algorithms. But before I get to a brief discussion of on versus off policy, I want to take a second and let's note, are there any things that from this RL problem that I've written down that are like different or shortcomings relative to the optimal control problem? There were a lot of parallels. I'll point them out again. We have S and A, the state set and the action set, as being parallels of U and X. We have the transition dynamics being the parallel of the like discrete time or continuous time dynamics F. And we have the value function being the sort of natural parallel of the value function. Is there anything that we wrote in that optimal control problem? I probably should have written them down. Is there anything else we can write down in that optimal control problem that we have not yet discussed for the RL problem? All right. I really meant to write this down, but typically we have something that looks like this in our optimal control problem. At least when we go to make it numerical, we will say, okay, whatever maybe constraints we had, we're going to write the constraints via some g of x less than or equal to 0. Or if you're, you know, in this school, you'll write it down as h dot of x greater than or equal to minus alpha h. But that's neither here nor there. Okay, constraints. Where is there? I don't know. I'm done asking questions. Adding constraints to RL, open problem. It's a problem that people always like, there will always be a bunch of papers on it, and then nobody will use any of those papers to do anything practical, right? The statement being that it is both hard and the current solution methods to it tend to dramatically negatively impact performance. The way that RL tends to handle constraints is by just giving a big penalty for violating the constraint. So if I violate the constraint, then you get a lot of cost, and the RL will learn to sort of not do that. But that is much different than actually enforcing the constraint in the way that you can in terms of an optimal control problem, where you can sort of have the optimal control problem actually make sure that it doesn't violate the constraint. If you're looking for a place to toss CBFs, this is a great example. If you can come up with a control barrier function, then you can just apply the control barrier function after the RL, or you can apply it in the RL training loop potentially. There's a bunch of places you can stick a CBF in order to sort of back out all sorts of very nice even proofs about the constraint satisfaction of the RL algorithm. So if CBFs call to you, they fit reasonably here and actually are a very natural bridge to helping you think about constraint satisfaction for an RL problem, for an RL program, which in general is a hard thing to do. So yes, constraints are sort of notably missing from this formulation. Yes. Well, I will first just posit that is actually a way to do it, right? So if I take the output of the policy and I put it through a CBF, I have a theorem that says that, look, the result will never violate the safety condition. I leave it open to you to come up with another way of doing that. I don't have one off the top of my head. So if I have an RL policy and I want to make sure that it doesn't violate some constraint, I can't like do it after because there's not a lot of structure there remaining. Okay, so I could try to do it before. Um, there's plenty of ways to think about this. Like you can come up with clever ways to enforce that the output of your neural network like always obeys some symmetry law or some like manifold constraint. Um, for instance, if you always need the output of your neural network to like lie on the unit sphere, you can enforce this constraint by just dividing the neural network's output by its norm, and then it lands on the sphere. So there are people that will call these like geometrically constrained neural networks, and really all they're doing is like dividing the neural network by its norm on the last layer, or fancier versions of that. But you can encode constraints actually directly into the policy, but that's not super flexible, right? There's most constraints that I write down for an RL problem won't like naturally lend themselves to structural constraints on the neural network. Um, so I think it is less, or I view it as less of like, oh, the CBUF is the best tool. And actually, in this case, it's one of the small number of tools that are very general. Like the idea is that if you can find a CBF, then you can put it in, and this is great. Now, how general is that? Like when can you find a CBF? Okay, well, we can never find CBFs for complicated systems anyway, so it doesn't really matter. It's also not general. Um, but we're arguing about like degrees to which a small number of methods that are trying to help this like big problem are working. There's not like a lot of other really good options out there. It depends. Do you care about constraints? It depends. So we talked, right? We have this structure versus stakes. RL is going to live all the time and work great in this low stakes regime. And it's because, well, in low stakes, we don't care about constraints, right? It doesn't matter if I like bump into the table when I walk by it. Like that's fine. Um, it doesn't, but does it matter that my Waymo doesn't like hit a pedestrian? Maybe more. And so now when you learn that your Waymo is like 80% driven by RL, and that RL definitely doesn't have any constraints in it, trade-offs. Yeah.
Are you talking about CBS in the context of safety filtering your policy output or enforcing a CBM constraint during, say, like training your RL?
Okay. Big can of worms that is not like related really to sort of vanilla RL, but is maybe very related to problems that we work on in our lab. So I want to make sure, disclaimer, we're now leaving the like broad RL community and we're diving into the like Amesy and Amber Lab RL community, which is no, no, no. It's like we just want to make sure that those are distinct, disjoint sets. There are no people that Blake, you can laugh. There are no people that are in like both of those sets, the general RL community and like the Ames RL community, right? Not strictly speaking true, but just let's make sure that we view these two things as separate. Um, you can stick the CBF wherever you want. Okay, option one, train the policy as you normally would, and then safety filter the output. You get some nominal amount of performance from the training at the beginning, and then you enforce safety on the back end. Problem, the policy doesn't know the CBF is coming. So it's taking its actions thinking one thing is going to happen, and the CBF is like, whoa, you can't actually do that. So you can get trapped, like you'll destroy all your performance. Option two, apply the CBF during training and after training. Now the policy basically can actually never take actions in simulation that violate the constraint because they get projected out, right? And then you do the projection again at the end, or you also deploy the my gosh, you also deploy the safety filter online. And now the policy was trained with knowledge of it, so it shouldn't be fighting it as much. And you get the guarantee on the back end from the CBF actually existing on the output. Um, while you're there, maybe toss in a penalty for the command that the policy outputs from violating the CBF, just so that you don't have the command like commanding a million in one direction and the CBF filtering that and giving you like one in the other direction. Like you might as well make those things kind of align with some sort of cost. Okay, now you've got like the standard CBFRL technique. Or you can try to do something more structural, like actually enforce that the neural network output obeys the CBF at like optimization time. So you can mess with the internals of PPO or the internals of any optimization algorithm to enforce that the policy pi actually physically obeys the CBF at any like time during training. Now, is this a good idea? Well, I'm giving the lecture, so I get to give my bias. No. Why is that a bad idea? Deep sigh. Okay, we're doing optimization. A large part of the like benefit of this optimization is random exploration. We're going to find good stuff to do by walking around and like discovering that stuff via literally random walks in parameter space. If I go into the internals of my algorithm and start snipping around and like cutting things out and moving things around, what that ends up happening is instead of taking a random walk in parameter space, I take like a projected random walk. So I'm going to draw like a very vague picture on the board. Right? So like, let's say that I have some like crazy cost landscape. Just like a, right? So, and then this is like the optimal point of my policy, but I've got some weird cost landscape. And then let's see, we'll say that my my safety constraint. All right, maybe I've drawn one that's too complicated. We'll just back up a little bit. Sorry. Okay, we're trying to get to the origin, right? This is like the optimal place in our policy space, and we've started, say, over here, right? And it may be that if I run standard PPO, the like random walk that I take through parameter space, like sort of looks like this, right? Vague claim. Let's say that I now enforce like safety on my policy space, and I do that by enforcing that I stay like over here, right? And notably, the optimal value of the parameters stays in the safe set. So like we can get to it. The problem is now PPO is actually not going to let this step happen. Like let's say there was a step where I jumped from here to here. PPO is going to say no, or constrained PPO is going to say, no, you can't do that. That new policy is actually unsafe. It violates the safety condition. And so what's going to happen is you're actually going to get projected like onto the constraint manifold. And now you're going to take another step, and PPO is going to be like, no, you can't do that. Not PPO. Constrained PPO is going to say, no, you can't do that. That's not safe. And so you get projected back. You've altered the path that your policy goes through in optimization space, and you've enforced that that path is safe at all times. Now, this has pros and cons. The pros is that you will actually get out a policy that obeys the optimization, sorry, that obeys the constraint. The reason that that's nice is that, and I mean that from a theoretical perspective, if I just say, if I have a proof that says the optimal policy is going to be safe, that's useless because PPO is not going to find the optimal policy. Maybe it'll find something close, right? But PPO is going to land in this circle, right? Or, I mean, it's actually not even a convex problem. So PPO is going to land in this circle or in like some other well over here that has similar cost. And so just because this dot, like the optimal parameters are safe, doesn't mean I'm not going to end up in this local minimum that's not. So if all that I have is that my like best possible policy is safe, then I don't get any guarantees. But if I can say that my policy is safe at every step of the optimization, then I know the policy will be safe at the end. But if I'm going to apply a CBF filter to the policy anyway, then I don't actually care that the policy is safe. The CBF is going to take care of all that. What I do care about is the fact that I've destroyed this like optimization path, and that lots of times the easiest way to get from one place to another in optimization space might be through a policy that is not safe in the interim, right? And there's really good examples of this. Like if I am doing stepping stones, right? So like there's discrete places that I can step on the ground, and I want to enforce those as a safety constraint, and I start standing, I will never be able to leave standing because the like next step of my policy needs to learn to like sort of stumble forward and like barely hit the first one and then like barely hit the second one and then miss and fall on the third one. And that will lead to more reward because I made 3 steps, but it's not going to be safe because I'm like not making all the steps. So what you're going to end up with is a policy that just learns to stand because you're going to project out any like potential progress step that violates your safety condition. So because I am not a safety person as much as a performance person, to me, this algorithm doesn't buy me much because I've have a high possibility in a practical sense of destroying my performance to enforce a constraint in the optimization loop that I might have been able to enforce afterwards with a CBF anyway. Yeah. Yeah, and then deploy CBF on the output. Exactly. Yeah, great approach.
Because there does seem to be like there are going to be like filters that are all like roughly within some epsilon level of the economy of each other. But one might have the dramatic like much more marginal safety than the other. So you kind of want your optics.
Yes.
Like you could like I could stepping stone, like I could have a rock that goes really fast and it goes on the edge of the rock. But I really want it to go.
Correct. Influencing like where the policy ends up is certainly a hard thing to do that is typically tackled by reward shaping. So I will pick rewards that encourage the kind of behavior that I want. But I think your idea about comparing this to the LLM and thinking about training stages is exactly spot on. I think this is like exactly correct. You let the optimization go as is, let it take its own path through optimization space. That buys you performance. And then now you want to impose safety, you do that second. Because if you try to impose safety right away, then you just destroy all your performance potential. Yeah. Okay.
Is that like more of an iterative approach? Like let it play out without that barrier. So like guy it.
Well, you just think of that. You let it run correctly 1,000 or a million data points for them. You feel like the LLMs is after you train the to spit out English, you want to all the questions to remember. So you go into a question answer curves, you get it in that. And then you add into your loss function some penalty for like going too far from what you originally created that. So the idea is you start by being like, what's the next word? And then you say, well, like that's landed in like vaguely the right place and optimization line. It's not like rigorous, but like I think it's kind of bullshit just to comment out this. But like you end up in vaguely the right spot of optimization line, and then from there you like freak yourself around, but you have some like strict penalty, make sure you're good.
Yeah, I mean, none of this is rigorous, right? We have a horribly complex optimization landscape, right? I drew something in R2, but let's remember this thing is in R like 8 billion for an LLM, right? So optimization landscape is really bad. I need to do literally everything I can to let stochastic gradient descent just go ham. And anything that I do to like shape the way that it goes is going to potentially alter where it ends up. And that can be good and bad. If I do that too early, then I risk basically like non-recoverable. I get into a part of the state space where I can never recover the performance that I would have if I sort of let the algorithm go free. Yeah.
your dynamics model around, try to get guarantees on convergence or something.
Yeah, a little bit. No, I mean, so I think our best approach in this regime was more on the reward shaping side. So there's a paper called CLFRL that shows how if you have like rewards of a specific structure, they can lead to better convergence properties. But in general, I would say that our lab is not great at algorithms. We don't really do almost anything algorithmic. And so the sort of algorithmic analysis that you're talking about, we haven't done a lot of. There is a little bit of work being done right now with safe algorithms, but yeah. Okay, I'm going to start wrapping up. If we have more questions, we can continue doing them as I'm erasing the board and stuff, but I do have to head out soon. So.